Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section of the class, we're going to cover a topic that everybody studies in calculus and a lot of people have problems with, and that section is called L'Hopital's rule. So if you look in your book and you look at the top, because x is approaching infinity, plug it in here. Okay, so what you're going to have is 2 to the infinity power, right? And then on the bottom, you're going to have infinity squared. So those are both big numbers, right? So you're going to say it's still the same form. It has a form of infinity over infinity. Because 2 to the infinite power is infinity. And certainly if you take infinity and square it, you're still going to get infinity. So you have the same problem here. You have infinity over infinity. You have some ratio of infinite numbers. And how do you know what this limit converges to? Does it converge at all? Okay, so here you have what we call two forms that you really don't have anything in your bag of tricks to go off and figure out how to do those, because they involve ratios of 0, 0 over 0, or infinity over infinity, and you just don't know how to do that. Let me give you one little teaser of what's coming up, and then we're going to jump right into L'Hopital's theorem, which is going to show you how to solve problems like this, and they're going to be like this, piece of cake problems, no problem at all. That is the following. Now notice that when you go off to infinity, let's say here, 2 to the infinity power, okay, and you have x squared, so you have infinity squared, okay? We have a limit that converges to 0 in this case if the two things approach infinity at different rates, okay? So I'm giving you a prelude because that's what L'Hopital's theorem is going to do for us. We're going to look at the derivatives of the top and the bottom function, and we're going to see how fast they approach infinity, because that's what a derivative is. It tells you the rate of change of something, how fast something is moving, okay? So we're going to look at the top and the bottom function, how fast they approach infinity, and that's going to tell us if the entire limit is going to exist or not, okay? Okay, so what I'm going to limit as x approaches the number a could be 0, a could be infinity, a could be 2.947, it doesn't matter, it's just a number. When you're taking the limit of f of x, some function of x, over some other function of x, that's why we denote the top one by f and the bottom one by g, because the top is one function and the bottom is another function. That limit is going to be equal to, as x approaches a, same limit here, and this is where it's going to blow your mind, the derivative of the top function divided by 2 3/2, right? So positive 3/2, and that's the answer, okay? So you see it's the same thing. We were approaching -1, and individually the top went to 0 and the bottom went to 0, so we had no idea what to do, but by taking the derivatives, L'Hopital's rule allows us to look at the rate of change of the top compared to the bottom to see how they converge together. So your in which they approached infinity. Okay, now let's switch gears a little bit and do a little bit different kind of problem. It's the same sort of thing. We still need to evaluate the limit, but I think you'll see that it's a little bit different. E to the minus x times the natural log of x. That's our limit we need to evaluate. What form is this? That's the first step you should always do when you're looking at evaluating these types of limits like this. Let's plug it in. What we would have is e to the minus infinity times the natural log of infinity. Okay? So put it into the form of L'Hopital's rule, then you can do the derivative of the top, derivative of the bottom, and from here on out I was just messing around with it to plug in the infinity here. Okay, now the next problem is, what if I had the limit as x goes to pi of the function x minus pi times the cotangent of x? Okay, the first thing to do is figure out what form is this, okay, what form is this? Well, if I put in pi here, I'm going to have pi minus pi, so I'm going to have 0, but what is this result? Is legal to use L'Hopital's rule. So, after we've done all of that, we just do it. Limit as x goes to pi. Now, what is the derivative of the top? X minus pi, take the derivative, is just going to be 1. Derivative of this constant number pi is going to be 0. Derivative of tangent is secant squared of x. Okay, secant squared of x. And I can rewrite this as the limit as x goes to pi of 1 over secant x squared. You're going to have to put one of them on the bottom. Now let's do one that we haven't done before. What if we have the limit as x goes to 0 of 1 over x to the 4th power minus 1 over x squared? Okay, what form do we have here? I think it's pretty easy for you to see. 1 over 0 to the fourth is infinity. 1 over 0 is infinity. You may have learned a long time ago that that was undefined, but something divided by nothing goes an infinite number of times. And you have minus 1 over 0 squared of 0. And don't forget the cosecant is 1 over the sine. And you can find that out from your rainbow. Sine, cosine, tangent, cotangent, secant, cosecant is 1 over sine. So you have infinity minus the sine minus 1 over the sine of 0. So what is this? Infinity minus 1 over sine of 0 is what? Sine of 0 is 0. So the form you have is infinity minus infinity. 1 over 0 gives you infinity. So you're in one of these indeterminate forms. It's the 0 times cosine of 0 plus sine of 0. And let's just do this and hope that we got something simpler. Okay? Cosine of 0 is 1. So you're going to have 1 minus 1 on the top. And on the bottom, you're going to have 0 times cosine 0. Cosine 0 is 1. So you're going to have 0 plus sine of 0 is 0. So you're going to have 0 over 0. Okay, so what have we found here? We have found that after we did L'Hopital's rule one time, we still ended up with a form of 0 over 0. So just like the simpler problems, if you get to the point where you're making progress, but you still have a form that L'Hopital's rule falls into, you just go ahead and do it again. And hopefully by taking derivatives, you'll make the thing simpler to the point where you will not have an indeterminate form. So we're on the right track. Let's do it again. We're going to use this guy as our starting point. We're going to continue taking derivatives and see what we get. Limit as x goes to 0. What is the derivative of the top? Derivative of cosine is negative sine of x, and this minus 1 is going to disappear when you take the derivative. 1 over natural log of 0. Okay, what is natural log of 0? Natural log of 0 is, think about it, natural log of 0 is e to the sum number is 0. Well, what number could that be? It's got to be negative infinity. Okay, so what you're going to have here is the form is going to be 0 to the 1 over negative infinity, which is going to be 0 to the power of 0. Okay, because 1 over infinity is going to give you the 0 up there, so you have 0 to the power of 0. And if you look over here, 0 limit of that beast, and I'm going to show you at the end that that's useful. Now remember back to your knowledge of natural logs back in wherever you learned it, trig or algebra or whatever. When you have the natural log of something raised to something else, that can be written like this: 1 over natural log of x times natural log of x. What you do is you take this exponent. When you have the natural log of something raised to a power, you can take the exponent out, stick it in front of the natural log like I've done here. This whole thing comes out in front, and then it's natural log of what's left over. That is something, the limit of this limit right here, which has a natural log wrapped around it. That is not the original limit you wanted to find. So all you have to do when you do this natural log trick is then say, okay, well the real answer then is e to the negative 2. You just raise the answer to the power of e to the power of your answer, and that's going to be it. Because what you're doing here is you're saying, you found the limit of the natural log of this thing, and if I had taken the original function and raised e to the power of all of this stuff right here, I would be finding the limit of what's inside here. So instead of carrying that through the whole